Today we're going to be doing section 1.9, the matrix of a linear transformation. In is an n by n matrix with ones on the main left right diagonal and zeros elsewhere. The ith column of in is labeled EI. So this is the I for identity matrix, E1, E2, E3. So the main diagonal is your ones. Note that the 3 by 3 identity matrix times x is the first column times x1, the second column times x2, and the third column times x3 would give you x. In general, for vector x and Rn, the identity matrix times x equals x. Let's look at example 1. The columns of the identity matrix 2 are 1, 0, 0, 1, and E1 is 1, 0, E2 is 0, 1. Suppose that T is a linear transformation from R2 to R3, where the transformation of E2 is 5, 0, 1, and the transformation of E1 is 2, negative 3, 4. Compute the transformation on X for any X, X1, X2. So X in R2 can be written as this. So x in R2 can be written as this. And we know that E1 and E2 are these. So it would be x1 E1 plus x2 E2. Our transformation on x would be the transformation of x1 E1 plus x2 E2. Remember, with transformations, we can pull out that x1 and it would be the transformation of E1 plus x2 times the transformation of E2. They told us the transformation of E1 and E2, so this would be x1 times 2, negative 3, 4 plus x2 times 5, 0, 1. And we know that this would equal, when we actually multiply it, 2x1 plus 5x2, negative 3x1 plus 0x2, and 4x1 plus x2. So I have my transformation of x equals 2, negative 3, 4, 5, 0, 1 times x1, x2 and then we know that this here is a and this is x. This is my transformation of E1, my transformation of E2, because this is right there, this is right here, and this equals AX. So to get A, replace the identity matrix with the transformation matrix. Theorem 10. Let the transformation T from Rn to Rm be a linear transformation, then there exists a unique matrix A, since such that the transformation of A equals AX for all X and Rn. In fact, A is an m by n matrix whose jth column is the vector transformation E sub j, where E sub j is the jth column of the identity matrix in Rn. So A would be the transformation of E1, E2, all the way to En. And this is the standard matrix for linear transformation T. So find the standard matrix for the linear transformation shown below. So that question mark, this right here, is the standard matrix linear transformation T. So what I would have to do here, I'm finding T of X, which equals T, the transformation of E1 and the transformation of E2, which if you look here, it'd be 1, 4, 3. Negative 2, 0, 2 times x1, x2. So my standard matrix would be 1, 4, 3, negative 2, 0, 2. In our final example, example 3, find the standard matrix of the linear transformation R2 to R2, which rotates a point about the origin through an angle of pi over 4 radians, counterclockwise. So this, just that you have your two diagrams, this is the transformation of E1, and this is the transformation of E2. And this is my theta here and my theta there. So first, let's talk about our transformation of E1. So if I'm looking here, my transformation would be my x and y coordinate. And we know that x would be cosine of pi over 4. And y would be sine of pi over 4. So we all know that's square root of 2 over 2 and square root of 2 over 2. My transformation of E2, when we're looking at this, you can think about it in more than one way, but if they're looking at, we're doing this counterclockwise, and you need to think of coterminal angles with this, and to get the same actual answer, I'm going to write my x-coordinate as negative sine of pi over 4, and then I'd have cosine of pi over 4. And this would give me negative square root of 2 over 2 and positive square root of 2 over 2. Which makes sense because look where it is. It's in the second quadrant. So A would be both of those together. Square root of 2 over 2, square root of 2 over 2, negative root 2 over 2, and positive root 2 over 2. And yes, I will take 1 over root 2 as the answers.